In this section of Module 2, we talk about using peripheral ICs with the 8085 microprocessor. In the previous modules, we have seen that we need to build an external circuit using discrete logic gates to interface the 8085 to I/O devices. These would be hardwired circuits and the designs are specific to each application. Here, we plan to use programmable peripheral interface chips which are designed to work with the 8085 and other microprocessors so that we have a flexible design which can be used for different microprocessor based products. These designs help reduce the work done by the microprocessor in order to talk to an I/O device. The standard chips used are the 8251, which is a communication interface called the USART. We'll look at that first, and the others are 8255, the programmable peripheral interface, 8279, the keyboard display interface, and the 8253, the programmable interval timer. So this slide shows the pin diagram of the 8251A, or the programmable communication interface. So as shown in the diagram, it is a 28-pin IC chip with pins 1 to 14 as shown on the left side and 15 to 28 on the right side. So we will go over all these pins in detail within a few slides, but for now you can just see that there are data pins D0 to D7, the 8 data pins which can be connected directly to the 8085. There is VCC, the power supply, reset and a clock, and ground, and RXC and TXC, which are the data, and a bunch of control signals which we will learn as we proceed. This peripheral IC is used for serial data transfer. So let's have a little background on what we mean by serial data transfer and what is its need. When it comes to transferring data from a microprocessor to the outside world, we have two options. It can be done parallelly or in a serial mode. So parallel communication means we're sending out the entire data word that's being put out by the microprocessor. So in the 8085, we will send out the data bits D0 to D7, 8 bits parallelly. So this would be the preferred mode, and it will be much faster than sending it out serially. So within the computer or within the microprocessor system, we would be connecting for short distances using a flat ribbon cable and parallel connectors, the microprocessor and the I/O devices like a printer or a disk. But if we want to transmit data over long distances, parallel data transfer would require too many wires. So usually we end up with a single wire or a pair of wires for sending data to much longer distances, like a telephone wire. So that's why we use serial data transfer. There are three methods for data communication. The first one is called simplex, where you can have data transmission only in one direction. So if you have two devices, A and B, A can send data to B. A is the sender and B is the receiver. B is not able to send data back to A. Or you can have something called half duplex, where communication can be done in both directions but only in one direction at a time. So A is able to send data towards B, B will receive it. After A says it's done, B is able to send data back to A and A can receive it. The third method is full duplex, where both A and B are able to send and receive data at the same time. We can also classify serial communication as synchronous or asynchronous transmission. In synchronous transmission, data is sent in blocks at a constant rate, which is defined by the synchronous clock, and start and end blocks are identified with specific bit patterns. We can also have asynchronous transmission, where we don't use a clock, and each data character has to be sent separately. So each character is identified by its start and stop bits, and they can be sent at any time. For sending serial data produced by the microprocessor or the computer over long distances, we can use the existing telephone system, which will make it very convenient. But telephone lines are meant to send audio frequency information, so around 300 to 3000 Hertz. So the digital signals which are coming out from the microprocessor at a higher clock rate cannot be directly sent over standard telephone lines. So these signals need to be converted to audio frequency tones. So the ones and zeros need to be converted to different frequency tones in the range that the phone lines can transmit. So the device used to do that is called a modem. So the modem stands for modulator and demodulator. It can convert digital signals to audio frequency tones and then reconvert the transmitted tones to the digital information. This slide shows the full picture of serial data communication between a sender and a receiver. In this case, on the extreme left, you can see a microcomputer controlled terminal which is talking to a large time-shared computer like a mainframe. So you want to send commands to the mainframe over telephone lines, and the mainframe will send back some display characters and things like that. So at the extreme left, you have the microcontrolled terminal, which is called a data terminal equipment. And on the extreme right, we have the timeshare computer, which is also called a data terminal equipment. And the DTEs on either side talk to modems, which are called DCEs or data communication equipment. And the modems communicate to each other across a telephone line by sending audio tones to represent digital data. So from the DTE to the modem, on the left you can see there is the TXD, which is the transmit data, serial data sent to the modem, and RXD, which is the receive serial data sent from the modem to the DTE. Similarly, on the right hand side at the other end, we can see TXD going out of the large timeshare computer to the modem, and RXD serial data coming into the DTE. The other signals are control signals used for communication and synchronization. Now that we have seen the basics of serial data communication, we will look into the 8251 programmable communication interface chip in more detail. In a previous slide, we have gone over the important data pins of the 8251 IC. Any programmable I/O device will have a control register to which the microprocessor can write an instruction, a status register that can be read by the microprocessor unit, the I/O buffer or register, some control logic, chip select logic, bidirectional data bus, handshake signals, and interrupt logic. The 8251 is a device which can be programmed for either synchronous or asynchronous communication. So it's also known as a USART or a universal synchronous asynchronous receiver transmitter. The USART relieves the microprocessor unit from the work of converting parallel words to serial bitstream data during transmission, and also conversion of the serial bits to parallel words of data during reception. It will also interface between the input and output ports and also synchronize data transfer between the fast microprocessor unit and the slower peripherals. The figure shows the block diagram of the 8251 IC. The boxes in red are the blocks which hold the data for sending or for receiving, and the boxes in blue are the control units. So on the upper left hand side we can see the data bus buffer, which has 8-bit data either coming in or going out from it. So that is D7 to D0 can be connected to the output pins of the microprocessor, and it's bidirectional. Either data is coming in to this chip or going out from this chip parallelly into the microprocessor. The data bus buffer is connected to the internal 8-bit data bus, and if you look at the top right hand side, the red box saying transmit buffer, that's the block which converts the 8-bit data which comes into it from parallel to serial mode and sends it out as TXD or transmit data to the modem. And the red box below it, which is the receive buffer, receives serial data on the pin RxD, converts it from serial to parallel, and sends the 8-bit data onto the internal bus. The transmit control block controls the transmit buffer. It has 3 signals. The first output signal is transmit data ready to the outside world, and TXE, which is transmit empty, or the buffer is empty, and the transmit clock input. On the receive side, there is receive ready, which is RX ready, going to the modem, and there is the RX clock and also a control input saying sync detect or break detect, which is for synchronizing the various characters being sent. The transmit control and the receive control have control lines internally generated from the read-write control blocks. The read-write control block has 6 inputs, which includes the reset and the clock inputs coming from the pins, and C bar D, which tells whether the data that's being written into this chip is a control word or is it data to be transmitted, and RD, which tells whether the data is being written into the chip, or WR, which tells whether the data has to be sent out from the chip. And there is a chip select, which helps us to select this chip by addressing. And there is control signals going into the modem control block, which are DSR, which is data set ready, DTR, data terminal ready, CTS, which is clear to send. And those are the main signals with which the 8251 is used. Serial communication is set up when the microprocessor programs the 8251 by using 2 control words. The first control word is the mode word, which specifies the general characteristics of the operation. The second control word is called the command word, which specifies the data transmission or reception. So the mode word is written immediately after reset. The following control word write will be treated as a command word. The format of the mode word is shown in this figure. The mode word has 8 bits, going from D0 to D7 in pairs of 2. The lowermost 2 bits specify the baud rate factor. The next 2 specify the character length. which is followed by 2 bits for specifying the error control, which is parity check, and then 2 more bits to specify the stop bit length. So if you look at the baud rate factor, the chip can be either in synchronous mode, in which case you don't vary the baud rate, or it can be in asynchronous mode, and you can set the baud rate to 1, 16 or 64 times the specified baud rate. The next two are the character length, which can set it to 5 bits, 6 bits, 7 bits and 8 bits. The following two are for error control. There is EP, which specifies even parity if it is 1, and 0 means it's odd parity. PEN means parity enable. So again, the bits are decoded and shown as disabled parity checking, odd parity, even parity, and disable parity checking. The start and stop bit lengths are given by the last 2 bits. So we can have 1 bit, 1.5 bits, or 2 bits. This slide shows the format for the command word. There are 8 bits going from D0 to D7. The lowermost bit is TXN. In all these cases, when a bit is set to 1, that function is enabled, and 0 means it's disabled. TXN is transmit enable, which enables the transmit part of 8251. 0 means it's disabled. DTR is sending the data terminal ready signal. 1 means a DTR of 0 is sent, which means it's active low, and 0 means DTR is not sent, that is DTR is set to 1. RXC is for enabling the receive part of 8251, 0 disables it. S break is for sending the break character on by sending a low signal on TXD. ER is for clearing all the error bits in the status board. So that's 1 means you're going to reset all the error bits. 0 means it's not cleared. RTS is for sending the request to send pin. 1 means RTS is being sent, so RTS is set to 0, which is active low, and 0 means RTS is not sent, that is RTS is set to 1. IR is for the internal reset. By writing a 1 into it, we can reset the 8251. If it is 0, then the 8251 is having normal operation. EH is for enabling the hunt mode. 1 will enable hunt mode and 0 is the normal operation. This slide shows the format for the 8-bit status word. The bits go from D0 to D7. The lowermost bit D0 shows TX ready, which is same as the value of the TX ready pin, and RX ready is the one that follows it, which is also same as the value of the RX ready pin. TXE or TXMT shows the same value as the TXE pin. Then followed by 3 error bits PE, OE and FE, where PE shows if there's a parity error in the transmission, OE shows the buffer overrun error, FE shows the framing error where you don't distinguish the start and stop bits correctly. The next one is the sync detect or break detect, which is same as the pin values for sync det and break detect. DSR shows the terminal DSR bar pin, where 1 means DSR is active or DSR is equal to 0, and 0 means DSR is not active or DSR equals 1.